We just raised another 425 million our Series F, invested in manufacturing, and then push our 7th generation prototype. So we built a lot of these systems to do fusion. That's a power bill that never arrives. Sounds like a meme until you remember the sun has been paying its own bill for 5 billion years. Fusion is the sun's trick, and a startup called Helion Energy wants to shrink that trick into a machine that makes steady electricity on Earth. Helion says it just raised about $425 million in a Series F round. Money meant to turn bold lab pulses into generators. The claims spark hope, hype, and doubt. Here is what Helion is building, how it works, and why the hardest part starts after ignition. The funding and the bet. Helion Energy is not trying to sell a cleaner version of today's power plant. The company is trying to build a fusion generator, a device that would make electricity without the usual detour through boiling water and spinning turbines. Reports about a Series F round of roughly $425 million matter because fusion work burns cash fast. The magnets, capacitors, sensors, vacuum systems, and safety hardware are complex, and prototypes do not come cheaply. A round of that size signals that backers believe the technical roadmap is at least plausible, even if success is not guaranteed. Helion's pitch also aims at a very specific prize: clean baseload power. Baseload means the steady electricity that keeps lights on when the wind drops and the sun sets. If fusion can supply that role, it could support grids that rely more on renewables without leaning on coal or gas. It could also reshape power for data centers and remote sites that need constant energy. In other words, the money is not just chasing a science project. It is chasing a new kind of infrastructure, one that snorts could challenge utilities, fuel suppliers, and the business models built around scarcity. Some fans jump straight to the home fantasy, a box in the garage that ends monthly bills. Helion itself speaks more carefully, because the first customers for any new generator are usually large buyers who can manage risk. Still, every big grid shift starts with one working unit that runs longer than anyone expects. For now, this funding is the fuel for that long test. Why fusion is different? Fusion is often described as the power of the sun, but the important part is what that means on Earth. In a fusion reaction, very light atoms are pushed together until they merge into a heavier atom. A tiny bit of mass becomes energy, and that energy can be harvested as electricity. This is not the same as nuclear fission, the process used in today's nuclear plants where heavy atoms split apart. Fission produces large amounts of heat, and it can create long-lived radioactive waste that requires careful management. Fusion, depending on the fuel and design, can avoid some of those burdens, but it is not magic, and it is not risk-free. The reason fusion has stayed in national labs for so long is control. The fuel must be heated to extreme temperatures so it becomes plasma, a super hot electrically charged gas. Then, it must be held in place long enough for atoms to collide and fuse. The plasma also wants to escape and cool instantly. Keeping it stable demands strong magnetic fields, precise timing, and materials that can survive intense conditions. That is why fusion is always described as almost here. The snort's science is clear, but building a machine that can repeat the reactions safely and cheaply is the hard part. The pulse machine inside Helion's approach stands out because it is pulsed and compact. Instead of trying to keep a steady burning plasma for long periods, the system works like a high-speed engine that fires again and again. The basic sequence starts with fuel. Helion talks about using deuterium, a heavier form of hydrogen along with helium-3, an isotope that can produce energy with relatively low neutron output compared with other fusion paths. The fuel is turned into plasma and injected into a chamber shaped like a long tube. Then the magnets do the main job. Electromagnets arranged around the chamber create fields that pinch and compress the plasma from both ends. In a short moment, that compression raises the plasma's temperature and density to extreme levels. Under the right conditions, nuclei collide and fuse, releasing energy in a burst of fast particles. This is often described as magnetic compression or magnetic pulsing, and it is the heart of Helion's design. A key concept is repetition. The machine must fire, harvest energy, reset, and fire again many times per second, while staying aligned and stable. That rhythm is what could make the device smaller than giant experimental reactors, yet still snorts powerful enough to matter. Electricity without the steam detour. Traditional plants waste a lot of potential by turning energy into heat first. Heat then becomes motion, and motion becomes electricity. Each step loses some energy, and each step adds cost and bulk. Helion claims its system can capture energy more directly. When the fusion pulse ends, the plasma expands and pushes against the magnetic field. That changing magnetic field induces an electric current in nearby coils. Following the same basic rule that drives generators and chargers, in this view, the reactor and the generator are effectively the same device. This idea is called direct electricity generation through electromagnetic induction. If it works at scale, it could mean less plumbing, fewer turbines, and smaller cooling systems. It also fits the pulsed style. A pulse creates a strong changing field which can create a strong electrical response. The output would still need power electronics to smooth it, often producing DC first and then converting it to AC for homes and grids. Helion's long-term vision suggests the generator could be compact enough to fit in industrial spaces and maybe one day be small enough for buildings or neighborhoods. That last step is where imagination runs wild, with talk of a garage-sized unit powering a home. The engineering bar, however, is not the size of the box. It is how long the box can run without failure. It must pulse with the same timing every cycle, and it must keep parts within safe limits. A few good shots are exciting. 1,000,000 good shots are a business. Fuel dreams, supply chains, and costs. Part of the excitement comes from fuel stories. Deuterium can be extracted from water, and the oceans hold an enormous supply. That makes it tempting to say the fuel is nearly endless. Helium-3, on the other hand, is rare on Earth, which is why some people point to the moon as a future source. Lunar mining makes for dramatic headlines, but it also raises practical questions about cost, access, and time. Helion supporters often argue that helium-3 can be produced through related fusion reactions inside the system, reducing reliance on off-world supply. Even if that idea works, it still has to be proven in long-term operation. Then there is the issue of what cheap really means. A fusion machine may have low fuel costs, but it can have high capital costs, strong magnets, fast-switching electronics, and precision parts do not become affordable overnight. Maintenance matters too. Coils heat up, components fatigue, and even small misalignments can degrade performance. On top of that are regulatory hurdles. Any device associated with nuclear technology will face licensing, inspection, and public scrutiny, even if it produces less waste than fish. Timelines also remain uncertain. Early prototypes can show promising signals, but a commercial generator must show repeatable net energy gain, predictable uptime, and a clear path to mass production. Those are business problems as much as physics problems. Hype, rumors, and what delays really mean. Fusion attracts the word free, and that word causes trouble. Electricity might become far cheaper if fusion succeeds, but it will not be free in the literal sense. Machines need factories, operators, repairs, and oversight. Still, the dream of near-limitless clean energy triggers a second storyline. The idea that powerful interests would rather keep people dependent on grids and fuel markets. Rumors of suppression follow almost every breakthrough claim in energy history. Helion's progress is a natural target for that kind of story, especially when the company talks. It's about dramatic performance milestones and when the broader public sees little change in daily life. But most delays in fusion have a more ordinary explanation. Extreme temperatures, stress materials, pulses that look great once must look great 1,000,000 times. A device that works in a lab must work in a supply chain, in a regulatory system, and in a market with competitors. Utilities also do not flip overnight. They plan decades, and they demand proven reliability. The most honest way to view Helion is as an experiment that has grown large enough to matter. The new funding suggests confidence, but it also buys time to face brutal tests. If the pulses become consistent and the costs fall, the conversation changes fast. Even small wins like longer component life or cleaner power output can stack up into a real breakthrough. If not, the story joins the long list of brilliant attempts that taught the world what fusion still demands. Helion's story sits between science fiction and hard engineering. The company has money, a clear concept, and a design that aims to turn fusion pulses into direct electric power. Yet, the gap between a promising test and a reliable product is where most energy revolutions slow down. If Helion can prove repeatable net gains, long lifetimes, and costs that compete with today's grid, the world will notice fast. Thank you so much for watching all the way to the end. If you enjoyed this deep dive, please smash that like button. Share your thoughts in the comments below, and don't forget to subscribe and turn on notifications.